This call is
So
now
we
being
had
recorded.
discussed the symmetry part and the lattice translation, primitive lattice vectors in the last class. So today we'll talk about three-dimensional Web's lattice and crystal systems. So two-dimensional we have already discussed. So now it is three-dimensional. So as you can see on the screen, uh, so all crystalline solids can be categorized into 14 different Web's lattices. 14. 14 basic Web's lattices types. Uh, all the crystal structure can be kind of defined by these 14 different Web's lattices. So these 14 Web's lattices fall under seven crystal systems. Seven crystal systems. Sorry, seven crystal systems. Uh, Number one is triclinic, next monoclinic, orthorhombic, trigonal or rhombohedral, hexagonal, tetragonal, and cubic. Okay, and then within those crystal systems, they have primitive, base-centered, face-centered, body-centered. Hmm. So I'll discuss what do we mean by base-centered, face-centered, body-centered. So let me come to the note. All right. So starting with so if let's say we have a normal unit cell like this, like this, then if we call, let's say, this to be x-axis and this to be y-axis and this to be z-axis, then our a vector or a1 vector is along x-axis. A2 vector is along y-axis. A3 vector is along z-axis. This is for cubic. This is for cubic. Okay. But if it is not cubic, then it will be this kind of three-dimensional object is called a rhombohedral type or a cuboid type in general. So if we try to describe the unit cell, what we need is for description of unit cell. Unit cell. First thing we need three sides. Three sides. Second thing we need is three angles. Three angles between the sides. Okay. So three sides, that means A1, A2, A3, these three sides, and angle alpha, beta, and gamma. So what is, if we try to understand what is alpha, so if we have three vectors, let's say A1, A2, A3. Then between A2 and A3, the angle is alpha. Between A1 and A3, it will be beta. And between A1 and A2, it will be gamma. All right. With that in mind, what are the possibilities? The first possibility is A1 not equal to A2, not equal to A3. Okay. A1 not equal to A2, not equal to A3, and alpha not equal to beta, not equal to gamma. So that means none of the sides are equal and none of the angles are also equal. So this kind of crystal structure is called a triclinic structure. Triclinic structure. Okay. One simple example is potassium dichromate. Potassium dichromate. Okay. This is called triclinic. So if we try to draw, that means if this is one side, this is another side, the third one will be another side. So all three are not equal. So it will be somewhat like, you know, like that kind of. All right. Next one would be one of the angles are equal. So what will it be? A1 not equal to A2, not equal to A3, but alpha equal to beta equal to 90 degree, but not equal to gamma. Alpha equal to beta, but not equal to gamma. And gamma not equal to 120 degree. Okay. So this kind of, so you can, this is the first one is completely arbitrary. A1 not equal to A2 not equal to A3, alpha not equal to beta not equal to gamma. Here A1 not equal to A2 not equal to A3, fine. But one of the angle or two of the angles are equal. Alpha equal to beta, which is again equal to 90 degree, and but it is not equal to the third angle gamma, and gamma is not equal to 120 degree. And this is called orthorhombic. Orthorhombic. What are the examples? Gallium, chlorine, iodine, bromine, gallium, chlorine, iodine, bromine. These have this kind of crystal structure. Well, these are gases, but when they kind of solidify, they will. The gallium is very pretty much solid at low temperature, so it will it will get orthorhombic structure. What is the next one? The third one. Third one will be no, sorry. This is monoclinic, not orthorhombic. Monoclinic. Let me rectify. This is monoclinic. Monoclinic. The next one will be orthorhombic. So A1 not equal to A2, not equal to A3, but alpha equal to beta equal to gamma. Alpha equal to beta equal to gamma equal to 90 degree. So that is orthorhombic. Okay. So what will be the next one? Fourth one would be the fourth one would be one of the sides will be equal or two of the sides will be equal. Huh? So true, that will be alpha or let me say A1 equal to A2 equal to A3. Hmm. Alpha equal to beta equal to gamma, but not equal to 90 degree and less than 120 degree. So then it is called trigonal. Then it is called trigonal. Okay. Number 5 would be A1 is equal to A2. A1 is equal to A2, not equal to A3. Hmm. And alpha is equal to beta. Alpha is equal to beta, 90 degree. And gamma not equal to 120 degree. Gamma is could be any angle, but gamma not equal to 120 degree. This is called hexagonal. This is called hexagonal. This is very important. Hexagonal. This structure is quite important. Hexagonal structure. So keep that in mind. A1 is equal to A2, not equal to A3. Alpha is equal to beta, equal to 90 degree, but gamma not equal to 120 degree. Sixth one is A1 equal to A2, not equal to A3, alpha equal to beta equal to gamma equal to 90 degree. This is called tetragonal. Tetragonal. Okay. Examples. Tetragonal example is titanium oxide. Titanium oxide is the example. Hexagonal silicon dioxide is hexagonal. Silicon dioxide is hexagonal. And the last one is all are equal. So A1 equal to A2 equal to A3 and alpha equal to beta equal to gamma equal to 90 degree. So this is called QB. This is called QB. So as you can see, we started with triclinic, then monoclinic, then orthorhombic, then trigonal, hexagonal, tetragonal, and then finally cubic. So somehow you have to kind of remember these relations for the 7 crystal systems. Then there are various types. Then there are various types. One is called types. Various types. One is primitive. Primitive. Second one is base center. Base center. Then third one is body center. Body center. And fourth one is face center. Face center. So what is the shape or what is the how does it look? The primitive or base center, body center, face center. So let us draw a simple cubic. Let us draw a simple cubic. So this is kind of simple cubic. If atoms or basis is only attached to the corners, only to the corners, only to the corners. You know, if atoms are attached or bases are attached only to the corners, only to the corners of the cube, then it is called primitive. Then it is called primitive. All right. Atoms are attached only
Sir,
to the,
primitive and simple. Sir, primitive and
yeah,
simple can be same.
yeah, it is kind of simple cubic. It is kind of simple cubic. Okay. But if it is not cubic, let's say simple cubic we are telling because the crystal type is, the crystal structure is cubic. This one. Okay. This one. But if it is not cubic, then what exactly we'll take? We'll call it primitive. That means, for example, let's take an example of first one. Let us take example of triclinic. Okay. Triclinic, what happens? A1 not equal to A2, not equal to A3. Alpha not equal to beta, not equal to gamma. It is like any general type. But here, if atoms only exist only at the corners, only at the corners, then it is called primitive cell. Then it is called primitive. Primitive triclinic. Okay, is it clear?
Yes, sir.
So next is, let's say we have another type where we have a tube cell. Now what happens if we have atoms at the corners first, atoms at the corners, and then we take the base. So we take the diagonal of the base. So this is one diagonal, this is the other diagonal. So this is one base. Another base is here on the top. So if another two atoms exist, one over here and one over here, not on other faces, not on other faces, only on the top and the down plane, then that is called base center. This is called base center. Okay, base center. Next one would be, if so, this is like uh, uh, base diagonal, midpoint of base diagonal, midpoint of base diagonal. There you have the atom. Okay. Next one would be, just draw like this. Here also again we'll draw atoms at the corners. And then what we will do, we'll take the body diagonal. Body diagonal. Let me write down as numbers. Yeah. So 1, 2, 3, 4, 5, 6, 7, and 8. So if I want to connect the atom 1 with 7, atom 1 with atom 7. So that will be my body diagonal. Body diagonal. The earlier case, it was the base diagonal. Now it is the body diagonal. So that means I'll connect 1 with 7, 1 with 7, 2 with 8, 2 with 8, 3 with 5, 3 with 5. eh? So that's intersection point. That intersection point, that is my body center. So this kind of structure where you have atoms at the corners, and one atom at the midpoint of body diagonal. Midpoint of body diagonal. Okay. So then it is called body center. Body center. All right. Next one is, let us draw it. So we have atoms at the corners. And then we have six faces, right? We have six faces. So if we take, for example, you take a Ludo dice. If you take a Ludo dice, there are six faces, right? 1, 2, 3, 4, 5, 6. Six faces. So similarly, it will have six faces. And if atoms exist on the face diagonal, so face diagonal, face diagonal. So midpoint of face diagonal, midpoint of face diagonal, if atoms exist there. For example, here, 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 similarly, here, here. So the difference between, so this is called face center, face center. Now difference between face centered and base centered is, in case of base centered, there are atoms only on the two faces. Whereas in face centered, there are atoms on all six faces. Okay, clear?
Yes, sir.
All right. So let me come to the, so here you can see actually how does it look like. For example, triclinic. You can see any general structure triclinic, simple monoclinic, base centered. Base centered, as I was explaining, one atom here and another atom here. So at the top surface and bottom surface, right? Uh, base centered, orthorhombic, simple orthorhombic, and base centered orthorhombic, body centered orthorhombic, and face centered. You can see how does the face centered look like. This is kind of, the screen is visible to everyone.
Yes, sir.
Yeah. So that's what I was drawing. Huh? Here one, 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 here one. Okay. 8 atoms. Then on this top surface one, bottom surface one, left surface one, right surface one, front surface one, back surface one. Okay. You getting?
Yes, sir.
Yeah. So similarly, hexagonal. Hexagonal, you can see the base is a hexagon. The base is a hexagon, and the atoms are at the corners as well as at the midpoint of the midpoint of the hexagon. Midpoint of the hexagon. Okay, midpoint of the hexagon. Yesterday I was telling that five-fold symmetry is not possible. I was telling five-fold symmetry is not possible. Okay, so just one minute. Hello, hello. Again. Again. Take it. Huh. Hello. Yes. Yeah. Coming back to five-fold symmetry. I was telling five-fold symmetry is not possible. So it is 1, 2, 3, 4, and 6. But five-fold symmetry is not possible. Okay. So why? Why five-fold symmetry? As you can see from the diagram, itself, if it is a rectangle, if it is a rectangle, then it can fill up the whole space. If it is a square or a triangle, it can fill up all the space. But if it is a pentagon, like here, there will be empty spaces. There will be empty spaces which cannot be filled by pentagons. Similarly, if it is a uh, instead of a hexagon, if it is a octagon also you will be having empty spaces. But as far as the definition of unit cell is concerned, unit cell is the smallest unit whose repetition will create the whole structure. But if the repetition of unit cell will create empty spaces, then it is not a unit cell. So that is why these five-fold and eight-fold symmetries are not possible. There is a very important question. I would like to discuss this example actually. It is telling prove that only 1, 2, 3, 4, and 6-fold rotational symmetries are possible in a crystal lattice. Only these are possible in a crystal lattice. Let us try to understand this question. What is it telling? Let us consider a linear array of lattice points PQRS. Linear array of lattice points PQRS on a lattice with lattice spacing A. So it is taking P, Q, R, and S, and at a distance A. Okay. Suppose the lattice has n-fold rotational symmetry. Lattice has n-fold rotational symmetry. If we rotate the segment PQ, and RS through angles phi n and minus phi n respectively, we obtain the segments P prime Q, and S prime, RS prime, or S prime R. Eh? Note here that P prime and S prime are also lattice points, and hence the distance between them will be an integral multiple of A. This sentence is quite important. Note that P prime and S prime are also lattice points, and hence the distance between them will be an integral multiple of A. We discussed in the last class when we try to go from one lattice point to another lattice point. Suppose we have one lattice point. Let me draw. Suppose we have one lattice point over here, another lattice point over here. So this is called lattice translation vector. Lattice translation vector. So this translation vector, if I denote it by T, this will be equal to some m times A1 vector plus some n times A2 vector plus some L or let's say Q times A3 vector, like that one. So where m, n, and q are basically integers. This is called lattice translation vector. So using that fact, it is telling you that if we have PQRS four lattice points and somehow we try to rotate PQ by an angle minus phi n and RS by an angle phi n, and we get new points P prime and S prime. Now P prime and S prime are equivalent lattice points. So that means RS should be equal to some integer times A. Let it be equal to MA. We draw perpendiculars QX and RY. QX and RY from Q and R respectively on the line PS. Now what will be cos phi n? This is phi n, right? So if, let me zoom it a little bit. So this angle is minus phi n, minus because it is in the opposite direction. So then this angle is also phi n. This angle will be equal to this angle because this line and this line are parallel. So in that case, if we take P prime x q, so cos minus phi n, which is equal to, cos is an even function. So it will be cos phi n will be equal to P prime x divided by P prime q, B by H, right? B by H. But P prime q is equal to A, since P prime q is simply rotated by PQ. This has been rotated to get this one. P has been rotated by phi n. So PQ must be equal to P prime q. And PQ is equal to A. So that's why P prime q is equal to A. If we use this relation and this relation, we'll get P prime x will be equal to A cos phi n. We'll get P prime x will be equal to A cos phi n. Similarly, P prime x is equal to A cos phi n. So ys prime or s prime y, that will also be equal to A cos phi n. So P prime S prime will be equal to what? P prime x plus xy plus ys prime. Now P prime x is equal to A cos phi n. This is A and this is again A cos phi n. So that will be equal to how much? 2A cos phi n plus A. 2A cos phi n plus A. But in general, it should be from this point to this point must be equal to some integer times A, because it is a lattice point. From definition of lattice translation vector, P prime S prime must be equal to MA. So that means MA must be equal to 2A cos phi n plus A, or M must be equal to 2 cos phi n plus 1. Alright. From this, we can calculate what is cos phi n. Cos phi n will be equal to m minus 1 by 2. But what is m? M is an integer. So m minus 1, if we denote m minus 1 to be capital N, this will just be n by 2. This will just be n by 2. Since cos phi n take values from minus 1 and 1, so n, cos phi n What is the value? Cos phi n minus 1 and 1, right? So n can take values. What are the values n can take? So this left hand side, this is important. Left hand side is cos phi n. What is the maximum value of cos phi n? Maximum of is 1. Maximum is 1. Minimum is minus 1. So this left hand side value will be in between minus 1 and 1. So for which values of n, this will be minus 1 and 1. So if we take n equal to minus 2, n equal to minus 2, then the value will be minus 1. N equal to minus 1, so it will be minus half because it is maximum is 1, minimum is minus 1. So in first case minus 2, for minus 2, for n equal to minus 2, cos phi is equal to minus 1. For n is equal to minus 1, cos phi is equal to minus 0.5. For n is equal to 0, this is again 0. For n is equal to 1, this is 0.5. For n is equal to 2, this is equal to 1. So only these 2, 1, 0, 1, 2. These are only possible. Okay. Okay. Now the angle phi n corresponds to these values of n are 180 degree, 120 degree, 90 degree, 60 degree, and 360 degree respectively. And if we convert it into fold symmetry, so then it will be 2-fold, 3-fold, 4-fold, 6-fold, and 1-fold. There is no 5-fold or 7-fold. So 5-fold and 7-fold are not possible in this case. So is it clear up to this point?
Yes, sir.
Okay. So I'll take 5 minutes break and then we'll start with the new part, crystal structure and cubic crystal, types of cubic crystal. All right. 5 minutes break. Okay, should we start now?
Yes, sir.
Okay. Yeah. So coming back to this is kind of recap of what we have already discussed. If we take a cubic crystal and we think about its symmetry, so what are the symmetries possible? So there will be reflection symmetry. That will be reflection symmetry, uh, and there will be inversion symmetry, rotational symmetry. Hmm. Inversion plus reflection. Inversion first, inversion then reflection. That kind of symmetry. And inversion and rotation. That kind of symmetry are possible. So five symmetry operations are possible. At this point, we just possibly have to remember. But later on, we'll see all these operations are kind of represented by some symbols, and those are kind of expressed in terms of groups. So when you study group theory, so they will be represented by some groups, and those group numbers will tell you what kind of symmetry or what kind of symmetry operations this crystal can go through. Okay, but at this point, I think we just have to remember that a cubic crystal can have reflection symmetry, inversion symmetry, rotation symmetry, inversion reflection, and inversion rotation. That kind of symmetry operations are possible. All right. Coming to different types of cubic crystal, just a few minutes back, somebody told, is it simple cubic? Yes, we'll be now focusing more on the cubic crystal type. So, cubic crystal have three types: simple cubic, which is primitive, simple cubic, another is body centered cubic, another will be face centered cubic. Okay, so simple cubic, body-centered cubic, and face-centered cubic. I'll take a pause here and go back to the book. There are very nice picture. I'll try to take some pictures from there and try to explain. Yes. So if all of you can look at, try to understand this picture. I'm using this book, Introduction to Solid State Physics by Charles Kittel. Okay. The diagram is visible to everyone?
Yes, sir.
Yeah. So what it has done in this diagram, let us try to understand. Okay. So here, here it has taken actually four simple cubic, no, sorry, body-centered cubic unit cells. Four body-centered cubic unit cells. Okay. So four body-centered cubic BCC cells. Okay. So as you can see, let us try to examine. Let us concentrate on the left one. One atom here, another atom here, another atom here, another atom here, another atom here, 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 and the body center. Yeah. Okay. Similarly, it has taken another, the next cell is kind of half visible. Another one is this one, 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 and this one. And the body center is here. All right. Now, if I take this corner atom, first corner atom, and connect this corner atom to one body diagonal onto the left, one body diagonal onto the right, and one body diagonal onto below. On you said, sir, what about the top one? No, the top one there will not be any, because this is kind of at the corner atom. It would have been the middle atom, then would have been the top one. So from this, if we take this atom to be origin, if we take that atom to be origin, then we take this atom to be origin, and we connect this atom with this one, and this one. That will create a primitive cell. That will create a primitive cell, because if you remember, a primitive cell is a cell where atoms exist only at the corners, where atom exists only at the corners. So then this A1, A2 and A3, this A1, A2 and A3 can be expressed like this, where x cap, y cap and z cap are the unit vectors along x-axis, y-axis and z-axis. You getting my point? All of you getting my point?
That
There
means
is
every other like BCC, FCC can be expressed as a primitive cell.
no. See, there are two concepts. One is your primitive cell, another is unit cell. Primitive cell is a cell where atoms exist only at the corners. Okay. If we take unit cell, it is possible that it could be primitive, it could be base centered, it could be body centered, or it could be face centered. So if we take a body centered qubit, we still can find a primitive cell, which will be a subset of this body centered cell. Okay. And primitive cell is the cell whose repetition, in sense, you will create the whole crystal. But for our understanding, better visualization, we are using a unit cell concept. But from crystal structure point of view, primitive cell is more important. Like we express the Wigner seed cell. Wigner seed cell does not look very good because it is kind of, perpendicular bisector from all nearest neighbor distances. But that Wigner seed cell, if repeated, that will create the crystal. Is it clear?
Yes, sir.
So these units, primitive cell vectors A1, A2, and A3 can be expressed in terms of unit cell dimension. So what is this relation is actually telling? That A1, which is this A1 is basically the primitive cell dimension, and it is expressed in terms of A, where small a is basically the side of the cube, which is basically the unit cell dimension. So left hand side it is the primitive cell, and right hand side it is the unit cell dimension. So it is kind of telling you that a primitive cell is related to the unit cell, but the difference is in a primitive cell, in the actual definition, as per the definition goes, the primitive cell has only one lattice point in a primitive cell. Whereas in case of unit cell, it could be 1, could be 2, could be 4, like that only. Okay. So A1 will be expressed as half of A, x cap plus y cap minus z cap. It is cyclic. Eh? If you go to A2, then your y cap plus z cap minus x cap. If you go to A3, it will be z cap plus x cap minus y cap. It is cyclic. So if you take sorry, if you take X, Y, Z and like that. So if first one is XY positive, then Z negative, then you take ZX positive, Y negative, or then you take so XY positive, Z negative, YZ positive, X negative, ZX positive, Y negative. So this way you can generate this primitive cell vectors. Where X cap, as it says, X cap, Y cap, Z cap are Cartesian unit vectors. Okay. So similarly, if you go to this picture, this is a face-centered cubic. This is a face-centered cubic. As you can see, I'll try to explain. You have one atom over here, another atom over here, another atom over here, another atom over here. You have one atom here, 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 and here. So 8 corners, 8 atoms, and then you have 6 face-centered atoms. One over here, top face, bottom face, left face, then the right face, and front face, and back face. Now this is unit cell. But if we try to construct the primitive cell means only atoms at the corners. Only atoms at the corners. In that case, the primitive cell vectors will be like this will be your A1, this will be like your A2, and this will be your A3. All right. So then what will be A1? A1 will be equal to half of A X cap plus Y cap. A2 will be equal to half of A Y cap plus Z cap. A3 will be equal to half of A Z cap plus X cap. And the angle between the axes is how much? Angle between the axes, which axis? Angle between the axes, these ones. Angle between the axes will be 60 degree. Angle between the axes will be equal to 60 degree. Okay? It is quite nicely explained over here. And this picture is basically about hexagonal structure where the primitive, you can imagine, you can see the hexagon. If you try to draw the hexagon, it is here, 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 and then similarly here, 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 like this, and then you try to kind of connect, like this. But then the primitive cell is somewhat shown in different way, where the shaded part, the blackened part is basically the primitive cell, where the primitive vectors are A1, A2, and A3. As you can see, A1 is equal to A2. The angle between A1 and A2 is equal to gamma, which is equal to 90 degree. A1 is not equal to, sorry, A1 is equal to A2, but not equal to A3. Not equal to A3. Okay. And the angle between A1 and A3 is beta. The angle between A2 and A3 is alpha. Alpha is equal to, so you can see here, A1 is equal to A2, not equal to A3, and alpha is equal to beta is equal to 90 degree, and gamma, which is basically equal to 120 degree. Okay. That part is quite clearly visible from here. Let me come back to your study material. Here. So it is telling simple cubic A1 is equal to A, A2 is equal to A, A3 is equal to A. Whereas in body centered, it will be A like this, or you can take that combination. Which one? Yeah, it is shown here over here. A1 is equal to A by 2, J cap plus K cap. So I cap, J cap, K cap. So these are kind of cyclic, you know, they're cyclic. So if J and K are positive, I is negative, then next what will happen? K and I will be positive, J will be negative. Next will be J and I and J will be positive, K will be negative. So this is how we define the primitive cell vectors. Similarly, face-centered cubic, you have face-centered cubic, you have A by 2, J cap plus K cap, K cap plus I cap, and I cap plus J cap. And diamond structure is kind of the hexagonal closed packing, HCP structure. The hexagonal structure we saw, that is kind of a diamond structure. Is this part clear up to this point?
Yes, sir. Sir, we need to repeat the unit cell to get the entire structure.
No, see, the difference between unit cell and primitive cell is if we repeat primitive cell, then also we will get the whole structure, whole crystal structure. Okay. But the primitive cell might be looking weird. Might not be looking very convenient, you know. Whereas if you take unit cell, it looks quite nice. Kind of, everybody wants to have a kind of cubic looking structure, you know. So it will be easier for us to understand. It will be easier for us. If we repeat unit cell, then also it will be a crystal structure. But primitive cell is kind of a subset of unit cell. Primitive cell is kind of a subset of unit cell. It's if sometimes it could be same. Primitive cell could be same as unit cell. Sometimes a primitive cell, as I shown you here, if you look at this diagram over here, see the larger one, the larger one, the larger one is the unit cell, whereas the smaller one inside it, that is the primitive cell. The larger one is the unit cell, and the smaller one which is inside it is the primitive cell. If we repeat this unit cell, then also we'll get the crystal. If we repeat this primitive cell, then also we'll get unit cell repetition ହେଲେ ବି हमको मिलिବ ଆଉ primitive cell repetition ହେଲେ ବି हमको मिलिବ କିନ୍ତୁ primitive cell ଟା repeat हमको ଦେଖିଲା ବେଳକୁ ଟିକେ weird ଦେଖାଯାଉଛି ମାନେ ତାକୁ visualize କରିବା conceptualize କରିବା ଟିକେ difficult. Whereas unit cell टाको बुझिबाटा हम ପାଇଁ बहुत सहज ହେଇପାରେ। ଆଉ यूनिट सेल ଆଉ ପ୍ରିମିଟିଭ ସେଲ ଭିତରେ ଅଲରେଡି ତ ରିଲେସନ ଅଛି ତେଣୁ ଆମ ପାଇଁ କିଛି ଅସୁବିଧା ନାହିଁ ତେଣୁ କହିବି ଯେ ସାର୍ ତାହେଲେ ପ୍ରିମିଟିଭ ସେଲ ବିଷୟରେ ଜାଣିବା ଦରକାର କଣ ପାଇଁ ଆମେ ଆଗକୁ ଯିବା ଯେତେବେଳେ ରେସିପ୍ରୋକାଲ ଲାଟିସ ପଢିବା ସେତେବେଳେ ୟୁନିଟ ସେଲ ଠୁ ପ୍ରିମିଟିଭ ସେଲ ର ଇମ୍ପୋର୍ଟାନ୍ସ ଅଧିକ ରହିବ ହେଲା।
Okay, sir.
All right. Next is Miller indices. Miller indices. कौन Miller indices? A crystal has various smooth faces with the same fixed angle between them. Each of these faces represent a particular plane in the crystal. Each of these faces represent a particular plane in the crystal. To identify these planes, we index them with 3 numbers. These numbers So what we do? We kind of index them, index the planes by 3 numbers. These numbers are called Miller indices of the plane. So in a crystal structure, what exactly is happening? Atoms are arranged in a regular manner. Atoms are arranged in a regular manner. If, for example, let me try to draw a very simple one. Let us say I have one point here, another point here, another point here, another point here, 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 here. So if I'm looking from this side, I'll be looking planes like this. I'll be looking planes like this, right? But if I'm looking from this side, then the planes will be somewhat like this. The planes will be somewhat like this. If I'm looking from this side, the planes will be like this, right? So from different angle of different perspective angle, we will have different planes, and these planes are part of the solid, but they are not same. Not same because the distance between the plane along this direction might not be same as the distance between the planes along this direction, and might not be the same as the distance between the planes along this direction. So that's how the planes are different, and that's why we need to kind of you know identify these planes, and to identify these planes, the planes are numbered with 3 indices. These indices are called Miller indices. Okay. To understand how a crystal plane is assigned Miller index, refer to figure 1.43. Let us try to understand what is 1.43. We have a plane. So HKL, let's say this is our plane. This is our plane. Okay. So what you will do? What we will do? First thing, the Miller indices of this plane are represented as small h, small k, small l. How do you find this small h, small k, small l? Now, first thing is if you have a plane, you try to find its x-intercept, its y-intercept, and its z-intercept. X-intercept, y-intercept, and z-intercept. Okay, it is telling you. It is here telling you very much clear. The Miller indices of this plane is HKL, which consists of three integers proportional to inverse of intercepts OH, OK, and OL. OH, OH, OH is the intercept along x-axis. OK is the intercept along y-axis, and OL is the intercept along z-axis. So OH, OK, OL, and then you take a ratio with respect to the lattice vector. With respect to the lattice vector. So OH by A1, and you take the inverse. OH by A1. So in definition, 1 by OH by A1. This is equal to small h. Similarly, 1 by OK by A2. This will be equal to your K. And 1 by, what was it? OL. OL by A3, which is equal to small l. This is how we find HKL. Or it is written A1 by OH, A2 by OK, and A3 by OL. How do you denote? You denote it by this kind of square. Open brackets. This kind of open brackets. Okay. So that's how we kind of find the Miller index of a plane. Miller index of a plane. And the distance between, as I mentioned in the, let's say, let me draw it again. Suppose I have one point here, point here, point here, point. No? So one plane over here, another plane here, another plane here. Yeah. So what will be the distance? These two, this distance between the or interplanar distance. If this plane has Miller index H, K, and L, H, K, and L, then the distance, the interplanar distance, it is expressed over here. The interplanar distance denoted by DHKL, having Miller index HKL, is given by this one. DHKL is equal to A by H square plus K square plus H square. H square plus K square plus H square. Okay? Is it clear? Miller index, how to find Miller index? Is this part clear to everybody? Am I audible? Am I audible?
Yes, sir.
ମୋ କଥା okay. ବୁଝି ହଉଛି ତ ନା କାହାକୁ ବୁଝି ହଉନି? ମିଲର ଇଣ୍ଡେକ୍ସ ମୁଁ ଜଷ୍ଟ କ୍ୱିକ୍ ରିକ୍ୟାପ୍ ଆଉ ଥରେ କରିଦଉଛି। ମିଲର ଇଣ୍ଡେକ୍ସ କେମିତି ବାହାର କରାଯାଏ? ତମେ ଗୋଟେ ପ୍ଲେନ ର x ଇଣ୍ଟରସେପ୍ଟ, y ଇଣ୍ଟରସେପ୍ଟ ଆଉ z ଇଣ୍ଟରସେପ୍ଟ ବାହାର କରିବ। ଯଦି x ଇଣ୍ଟରସେପ୍ଟ ଟା OH ହେଲା, y ଇଣ୍ଟରସେପ୍ଟ ଟା OK ହେଲା ଆଉ z ଇଣ୍ଟରସେପ୍ଟ ଟା OL ହେଲା, ତାହେଲେ ତାକୁ ଆଗ ଡିଭାଇଡ କରିବ କାହା ଦ୍ୱାରା? ଲାଟିସ୍ ଭେକ୍ଟର A1, A2 ଆଉ A3 ହେଲା। ତାହେଲେ ବାହାରିବ କଣ? OH by A1, OH by OK by A2, OL by A3। ଯେତିକି ବାହାରିବ ତାର ଇନଭର୍ସ ନେଇଯିବ। ତାର ଇନଭର୍ସ ନେଇଗଲେ ଯୋଉ ନମ୍ବର ରେସିଓ ନମ୍ବରଟା ବାହାରିବ, that will be your HKL. But the important part here is let me work out one problem, then possibly you will be able to understand. Suppose I have a plane like this. I have a plane like this. Right? ये भड़िया गोटे प्लेन के अच्छी। Okay? তাহলে যদি তার x ইন্টারসেপ্ট বাবা, তার মানে এইটা হচ্ছে তার x ইন্টারসেপ্ট। দিস ইজ ইটস x ইন্টারসেপ্ট। x অ্যাক্সিস, তো এটা যদি x অ্যাক্সিস, এটা যদি y অ্যাক্সিস আর এটা যদি z অ্যাক্সিস, তাহলে এইটা হচ্ছে তার x ইন্টারসেপ্ট। x অ্যাক্সিস কে এই থেকে কাটিছি, সে কাট করেছি। দিস ইজ ইটস y intercept, this is its z intercept. Okay, let us call this to be O and this to be H, this to be K and this to be L. Nahi? Suppose तारो OH ABC A1 along x-axis, A2 along y-axis and A3 along z-axis are the lattice vectors. Suppose OH is equal to 3A1. OK is equal to 6A2. Now OL is equal to 0.5A3. Let's say. তাহলে প্রথমে কোন করিবা আগ রেশিও তাহলে H is equal to how much 1 by OH by A1. So this will be equal to 1 by 3A1 by A1, which will be equal to 1 by 3. K. K টা কেতে 1 by OK by A2. This will be equal to 1 by 2A2, no, sorry, 6A2. 6A2 by A2, this is equal to 1 by 6. L will be equal to 1 by 0.5 A3 by A3, which will be equal to 1 by 0.5, which is equal to 2. Now HKL would be equal to what? 1 by 3, 1 by 6, 2. But we do not write HKL in terms of fractions. So what we do? What exactly we will do? We'll take. So this is like how much? 2 by 6. This is 1 by 6, and this is 12 by 6. So 12 by 6. So then we will write it is equal to 2, 1, and 12. 2, 1, 12. Okay. So HKL values are 2, 1, and 12. Is this part clear to everybody?
Yes, sir.
Okay. All right. So then I think move over to the next part. Quasi-crystals and liquid crystals. Quasi-crystals are like they are not fully completely crystals, but they are kind of half crystals. So the ordering will be in some patches it will be highly ordering, and some patches it will not be. So it is quite evidently explained over here. Quasi-crystal is essentially crystal-like substance. Quasi-crystal is essentially crystal-like substance in which the geometrical arrangement of atoms exhibit long-range order, but unlike crystal in which atoms are arranged in a repetitive pattern, quasi-crystals consist of atoms that are arranged in a pattern that does not repeat itself. So long-range order will there will be long-range order, but repeat long. There will not be proper repetition. So here, like we have infinite repetition. Whereas in liquid crystal, this is oxymoron type concept, liquid crystal. So here, liquid crystals are materials. Liquid crystals are materials which crystal like order structure, but are in fluid in nature. Their ordering is there, repetition is there, but it is more like a fluid. It is not liquid, complete liquid. It is more like a fluid, so it can flow. It is not completely hard, solid substance. At the microscopic level, these materials consist of rod-shaped molecules. This is off, not on. These materials consist of rod-shaped molecules, organic materials which have permanent dipole moment. So, how exactly they are ordered? Because of their dipole moment, and can orient themselves parallel to each other. ତାମାନେ କ'ଣ ଏଇଭଳିଆ ହେଇକି ରହିବ ଏଇଭଳିଆ ହେଇକିରି ordering ହେଇକିରି ରହିବ. Yeah, there is no much mathematics involved in it. Just for description type. we can possibly understand. I think that's not an issue. I think everything is clear up to this point.
Yes, sir.
First part, yeah, you can work out these problems, short problems, and long problems. I'll take 5 minutes break and then I'll start with reciprocal lattice and X-ray diffraction. Okay. Okay, let us start with something very interesting. The next part, which is reciprocal lattice and crystal structure determination by X-ray diffraction. So, reciprocal lattice, what is uh, reciprocal lattice or what is reciprocal space? Let us try to understand what is being written over here. It is telling you we are now familiar with the geometrical arrangement of atoms in Unit 1. You must have noticed that the geometrical configuration or interatomic distances are defined in three-dimensional real space. Important part here is real. Three-dimensional, three-dimensional represent the crystal lattice. He is asking, is there another way to represent the crystal lattice? The answer to this question is affirmative. Yes, we can also represent or express the same arrangement in another way, what is called a reciprocal space or reciprocal lattice, where the reciprocal space units are in length, meter inverse, meter to the power -2, meter to the power -3, like that one. The concept of reciprocal lattice, the concept of reciprocal lattice also simplifies the representation of parallel crystal planes. Parallel crystal planes. So what is it telling you? That it is not only so in unit 1, whatever we discussed for crystal structure, that is not the only way we can define crystal structure. There is another way of defining the crystal structure, that is in a reciprocal space, where the reciprocal space units are meter inverse, length inverse. Okay, all of you are familiar with Fourier transform. ସମସ୍ତେ Fourier transform ବିଷୟରେ ଆଇଡିଆ ଅଛି ତ?
Yes, sir.
So ସେଇଟା ଟିକେ ଯଦି ଭୁଲି ଯାଇଥିବ ସେଇଟା ଟିକେ ରିଭାଇଜ କରିଦେବ, କାରଣ ଏ ରେସିପ୍ରୋକାଲ ଲାଟିସ୍ ପଢିଲା ବେଳକୁ Fourier transform କଥାଟା ମନେ ଥିଲେ ଆମେ ଇଜିଲି ସେଟାକୁ ମ୍ୟାଥମେଟିକାଲି ବୁଝିପାରିବା। Fourier transform ରେ ବି ସେଇ ଭଳିଆ ହୁଏ, ମାନେ ରିଏଲ ସ୍ପେସ ଟାକୁ ତାକୁ ଆମେ ରେସିପ୍ରୋକାଲ ସ୍ପେସ କୁ ନେଇଯାଉ। ଓକେ, ତେଣୁ the outcome of this unit will be to represent different crystal vector lengths in reciprocal lattice space, obtain reciprocal lattice for a given direct lattice, determine reciprocal lattices for FC, simple cubic, FCC and BCC crystal, and then describe something what is called Brillouin zone in reciprocal lattice space, which will be very much useful while discussing about band structures. And then state why X-ray is appropriate to determine crystal structure. Why can't we just see the crystal structure using normal light, visible light? Why do we have to use X-rays? And how Bragg's law follows from Lau treatment. These are the things we will be discussing. But first and foremost, construction of reciprocal lattice. Construction of reciprocal lattice. How exactly reciprocal lattice is constructed? Let us try to focus on that. It is telling, let us now learn to construct the reciprocal lattice. How? It shows a single family of infinite parallel and equidistant planes. This picture over here, this picture over here, this one, what is it showing? It is showing many parallel equidistant planes which are extending up to infinity. Something like, you have one plane, and then you have another plane, then you have another plane, and you have another plane, and another plane. It is kind of going on. So infinite number of planes are being shown over here. Okay, and these planes will be characterized by their index HKL, because in the last unit we understand that each plane can be assigned and three index or three numbers which are called Miller indices, and the Miller index can is HKL, and the distance between two such planes, distance between two such planes is DHKL. DHKL. Okay, it is telling now let us choose origin of coordinate axis at any arbitrary lattice point. Let us choose origin of coordinate axis at any arbitrary lattice point. Say O. Which take the origin to be at O. Okay. And draw a common normal. Okay. Draw a common normal OA to these planes from this point. So what you do, you have set of parallel planes. You take any arbitrary point O as origin and draw normal to the this plane, and that normal is OA. Okay, then the point M on this normal, which is located at a distance inversely proportional to the interplanar spacing from origin, defines the reciprocal lattice point. तामाने कौन है यदि हमें और टिके सहज भाव में बुझा पे चेष्टा करिबा हमें कौन करिबा पैरेलल सेट ऑफ पैरेलल प्लेन्स नबा प्लेन गुडा सब पैरेलल हे कि अछंती इक्विडिस्टेंट हे कि अछंती प्रत्येकटा प्लेन रो गोटे मिलर इंडेक्स अछि HKL आउ गोटे प्लेन इंटरप्लानर स्पेसिंग होछि DHKL वर्तमान हमें कौन करिबा जे कोनोसी गोटे पॉइंट नबा आ सेही पॉइंट रू हमें जो ये जो प्लेन गुडा पैरेलल इक्विडिस्टेंट प्लेन अछि ता उपरको गोटे नॉर्मल टे ड्रॉ कर सेही नॉर्मल डायरेक्शन रे हमें आउ गोटे वेक्टर नबा आउ गोटे पॉइंट नबा m जोटी कि OM टा हबो 1 by DHKL 1 by DHKL. Okay, the vector joining the point O and M is called reciprocal lattice vector. These for these planes, if we consider the special case of family of planes defined by Miller indices 0, 1, 0, the orthogonal lattice space as shown in figure, the reciprocal lattice M would be located at a distance C divided by D 0, 1, 0. Okay, this is how we are constructing. So जो parallel plane अच्छी तार perpendicular direction रे इंटरप्लानर डिस्टेंस रो इनवर्स जति की होबो सेति की डिस्टेंस नै कि हमें आ गोटे लैटिस स्पेस क्रिएट कर परिबा व्हिच इज बेसिकली कॉल्ड रेसिप्रोकल लैटिस स्पेस. इज इट क्लियर? If it is not clear, you can ask me. Let me show you few figures from the book. Yeah, if you see this figure, this is a primitive cell or unit cell in a reciprocal space. A reciprocal space रे भी ए भले unit cell करके हमें crystal structure को देखी परिबा है. This group doesn't have the reactions. Back to your. Actually, basically, এই ফর্মুলা তক টিকে মনে রাখবো। This is represented by star. If A3 star means it's a reciprocal lattice vector in the z direction. A1 star means it is reciprocal lattice vector in x direction, and A2 star means it's reciprocal lattice vector in a y direction. समस्त टिके এই তিনটা ফর্মুলা টিকে মনে রাখবো। How to calculate reciprocal lattice vector কি লিখব মনে রইব? ବୁଝି ହଉଛି ନା ବୁଝି ହଉନି? এটা ବୁଝି ହଉଛି ତ? Am I audible?
Yes, sir.
Yes, sir, audible.
Audible. ବୁଝି ହଉଛି ତ ନା କିଛି ଅସୁବିଧା ହଉଛି?
Yes, sir, ବୁଝି ହଉଛି।
ବୁଝି ହଉଛି। এই ফর্মুলা টিকে মনে রাখব কারণ প্রবলেম পচারা যাইপারে। ମୁଁ ଗୋଟେ প্রবলেম টি just I'll try to work out. Let me see if they have already solved this or not. Otherwise we can. Yeah, they have done actually. Okay. Let us try to see. If you have a simple cubic structure, find out the reciprocal lattice vectors. Simple cubic रे कौन होची? A1 is equal to A2 is equal to A3. Let's say it is equal to A, and alpha is equal to beta is equal to gamma is equal to 90 degree. This is our simple cubic. So that means कौन लिखी होगा? A1 is equal to A I cap, A2 is equal to A J cap, A3 is equal to A K cap. This is coming from crystal structure. This is coming from crystal structure. From here, we can write A1 is equal to AI cap, A2 is equal to AJ cap, A3 is equal to AK cap. Right? ठीक था? ताले A1 star टा कितने होगा? A1 star will be equal to some constant C times A2 cross A3 by A2 cross A3 dot A1. So this is kind of a box product volume. eh? So then that will be equal to how much? A2. A2 is AJ and A3 is AK. J cross K is equal to I. So A square I by A cube I dot I. So that will be equal to 1 by A I cap. 1 by A or C by A. C is a constant. So that's why similarly A2 will be equal to C into J cap by A. A3 star will be equal to C K cap by A. So you can see 1 by A, 1 by A, 1 by A. So it is a reciprocal of A. That's why it is called reciprocal lattice. Similarly, if you have face-centered cubic, we can work it out. We can work it out. Let us work it out. Let's say we have face-centered cubic. Face-centered cubic. So then, my A1 will be equal to what? A1 will be equal to what? A by 2 J plus K, right? J cap plus K cap. A2 will be equal to A by 2 K cap plus I cap. And A3 will be equal to A by 2 then I cap plus J cap. A1 star will be equal to some constant C times A2 cross A3 by A1 dot A2 cross A3. Right. Now, what is A2 cross A3? First, I have to find out what is A2 cross A3. That will be equal to what? All of you know how to find out, right? Or let me A by 2 K cap plus I cap cross what is that? A by 2 square, and then A3 is I cap plus J cap. So A by 2 square. So K cross I, J, K. K cross I will be equal to what?
J cap.
J. J.
Yes, sir.
So
J cap.
K cross I will be equal to J plus K cross J. K cross J will be equal to minus I.
Minus I cap.
Right? This is going
Yes, sir.
minus I. I cross I 0. I cross I 0. And I cross J is K.
K cap.
Right? So as you can see, this is A by 2 square minus I cap plus J cap plus K cap. Right?
Yes, sir.
Alright. Yeah. And the volume that you can actually find out A1 dot A2 plus A3. If you find out, this will be A by 2 to the power 3. That you will get. You can verify yourself. Okay.
Okay, sir.
Yeah. So then what exactly we are getting? A1 star is equal to 1 by or 2 by A by 2. So that will be 2 by A minus I cap plus J cap plus K cap. Okay. Similarly, you will get A2 star will be equal to 2 by A. So I cap. So here it was first one is minus J cap positive. Now what will you get? Next J will be negative, IK will be positive, and A3 star will be equal to 2 by A. I and J will be positive, K will be negative. By symmetry, I am writing. Okay. As you can see, this is somewhat looking like a BCC structure. This is somewhat looking like a BCC structure, isn't it? Because BCC
Yes.
structure
Yes,
ଏଇଭଳିଆ
sir.
ଥିଲା ତେଣୁ ରେସିପ୍ରୋକାଲ ଯଦି ରିଏଲ ଟା ଫେସ୍ ସେଣ୍ଟର୍ଡ ହେଲା ତା ରେସିପ୍ରୋକାଲ ଟା ବଡି ସେଣ୍ଟର୍ଡ ହବ ଆଉ ଯଦି ରିଏଲ ଟା ବଡି ସେଣ୍ଟର୍ଡ ହେଲା ତାହେଲେ ତା ରେସିପ୍ରୋକାଲ ଟା ଫେସ୍ ସେଣ୍ଟର୍ଡ ହବ ହେଲା that part has been explained over here you can check it out huh? So I'll possibly stop it here. If you have any doubt, you can ask. Next class, I'll start with Brilliant John. Brilliant John and then X-ray diffraction. If you have any question on reciprocal lattice or the first part, you can ask.
Sir, why we need to find a less reciprocal lattice? Means it will be used later, or only we have to find it here?
Yeah, it's a very good question actually. See, when everything is very much easy in a real space, everything is easy to understand in real space. Why are we interested in reciprocal space? Isn't it? The
Yes, sir.
answer is when we are trying to see a crystal, what exactly we are using? We are using some form of light. In this case, we are using X-ray. I will also come back to that. Why X-ray? Why not visible light like our tube light or like LED light also? Why can't we see through a crystal using our LED light? We cannot. That we'll discuss. But the idea is to see a crystal, to know its structure, we are using some form of light, right? That means it is energy. Now, energy when it interacts, with the energy when it interacts with a crystal, it interacts in the wave number K, not in wavelength form. It, you all of you know E is equal
Yes.
to h nu, right? E is
Yes,
equal
sir.
to
Yes, sir.
h nu frequency, isn't it? And
Yes, sir.
frequency is equal to how much? C by lambda, right? Or what is it?
Yes, sir.
Frequency is equal to C by lambda, right?
Yes, sir.
So it is somehow lambda is real space dimension in meter, right? And energy somehow is kind of interacting in inverse of wavelength, isn't it? Energy is interacting with the system in inverse of wavelength. So if there would have been something inverse of wavelength, then it will be the interaction will be kind of direct. ଆମେ ଯଦି ସିଷ୍ଟମ ଟାକୁ ଡାଇରେକ୍ଟ ଦେଖୁଛେ ଆଉ ଏନର୍ଜି ଟା ଯୋଉ ଇଣ୍ଟରାକ୍ଟ କରୁଛି ସେ ଇନଭର୍ସ ରେ ଇଣ୍ଟରାକ୍ଟ କରୁଛି ଆମକୁ ସୁବିଧା ହୁଅନ୍ତା ଯଦି ଆମର ଏଇ ଯୋଉ ଡେସ୍କ୍ରିପସନ କ୍ରିଷ୍ଟାଲ ଡେସ୍କ୍ରିପସନ ଟା ବି ଇନଭର୍ସ ରେ ଥାନ୍ତା ତେଣୁ ସେଇଟା ଆସିବ ଯେତେବେଳେ ଆମେ ଲାଉ କଣ୍ଡିସନ ଡିସ୍କସ କରିବା ହଁ ସ୍କାଟରିଂ କଣ୍ଡିସନ ଡିସ୍କସନ କରିବା ସେତେବେଳେ ଜଣା ପଡିଯିବ ଯେ ଆକ୍ଚୁଆଲି ଇନଭର୍ସ ହେଲା ବେଳକୁ ମାଥମେଟିକ୍ସ ଟା ପୁରା ସହଜ ହେଇଯାଉଛି मैथमेटिक्स टा बुझिबा ପାଇଁ जो मैथमेटिक्स टा ସେଟା ପୁରା ସହଜ ହେଇଯିବ whereas डायरेक्ट स्पेस ହେଲା ବେଳକୁ ଆମକୁ ଗୁଡାଏ କଷ୍ଟ କରିବା ପାଇଁ ପଡୁଛି ଠିକ ଅଛି
Okay, sir.
इट इज बेसिकली फॉर अंडरस्टैंडिंग ସେମିତି as such ଗୋଟେ reciprocal lattice କୋଉଠି ରହିଛି ଆଉ डायरेक्ट lattice ରହିଛି crystal is there it is how we are looking at it ଆମେ डायरेक्ट स्पेस रे रियल स्पेस ରେ ତାକୁ ଦେଖୁଛୁ ଆଉ ତାକୁ ଇନଭର୍ସ କରିକି ଦେଖୁଛୁ ବିକଜ ଆମେ ଯୋଉ ଦେଖୁଛୁ ବୋଲି କହୁଛୁ ଯାହା ଦ୍ୱାରା ଦେଖୁଛୁ यूजिंग एक्स-रे डायफ्रैक्टोमीटर इट इज एक्चुअली सीइंग इट इन रेसिप्रोकल स्पेस पुणी हमको अवसर कन्वर्ट करिया ପାଇଁ ପଡୁଛି रियल स्पेस शेयर न करिକି ଯଦି रेसिप्रोकल स्पेस रे ଆମେ ଚିନ୍ତା କରିବା ତାହେଲେ इंटरेक्शन विल बी डायरेक्ट ହେଲା
Okay, sir.
एनी अदर डाउट नो
No, sir.
okay if not then I'll possibly stop it here we'll start tomorrow same time and the topic will be drilled one okay
Okay, sir. Good night, sir.
okay have a good time